Good morning, everyone.
Good morning, sir.
Okay, so we'll learn another simplex method. It is called dual simplex method. Now, since I'm introducing dual simplex, all the simplex method you have learned earlier are called simplex method. Okay, primal simplex method. But if simply simplex method is mentioned, that simply refers to primal simplex. So simplex method, whenever it is mentioned anywhere, assume it is a primal simplex method until unless it specifically says a dual simplex method. And when I say simplex, it is whether algebraic form, tabular form, or revised simplex, whatever you say. So dual simplex method actually makes life easier for all the ill-behaved kind of problem. For example, we have suppose a problem minimize, and we can work with maximization also. Finally, we'll convert into any minimization problem into maximization to solve it as our standard form. But any greater than equal to constraint can be converted because it allows negative RHS. So a dual simplex method is invoked only when you have a negative RHS, then you can invoke. So suppose if I give you a constant x1 plus x2 greater than equal to 3, right? To convert it in our standard form, what we'll do, minus x1 minus x2 is less than equal to minus 3. You can use dual simplex. Now suppose a method is, so ideally no artificial variables are required. You can solve it as a what we will see like a normal simplex method only. Second thing is, suppose there is a constraint x1 plus x2 equals to 1. How can we work with this kind of constraint? So convert into two constraints, x1 plus x2 greater than equal to 1 and minus x1 minus x2 is less than equal to minus 1. So this represents the x1 plus x2 equals to 1. Now further, you can convert x1 plus x2 greater than equal to 1 into a negative constraint and you can proceed with the, sorry, not x1, my bad, minus x1, x2. x1 plus x2 less than equal to 1. x1 plus x2 less than equal to 1 and x1 plus x2 greater than equal to 1. In what condition it will happen? When x1 plus x2 equals to 1. Now this equal greater than equal to constraint, you can convert it to minus x1 minus x2 less than equal to minus 1. So when you are solving dual simplex method, things to keep in mind, it should be, you have to convert into a maximization problem. All constraints should be converted as less than equal to type, whether greater than equal constraint you have, less than equal to constraint you have, and you should have a negative right hand side or b value, then only you can invoke dual simplex method. Is it clear? Any questions so far? So ideally this takes care of any kind of ill behaved problem which we have seen using two phase or big M. All those methods we can work with dual simplex without using any artificial variable. Now coming to dual simplex method. Simplex method, as I was explaining you earlier, is a primal algorithm. Where it maintains primal feasibility. And works towards dual feasibility. So I was explaining you with the primal simplex algorithm, your right hand side at any point of time, any iteration is always greater than equal to 0. But if you look at the dual variable value, which is below the slack variable in the zeroth coefficient, what you will realize that was not feasible. The moment dual values also become feasible, you are at the optimality. So that is for primal. When it comes to dual simplex algorithm, it works with dual feasibility. It maintains dual feasibility. And works towards primal feasibility. So what is your understanding with this statement? It maintains dual feasibility and it maintains dual feasibility iteration after iteration and works towards primal feasibility. What do you understand by this? Given that you already know simplex algorithm maintains primal feasibility and works towards dual feasibility. So what is your understanding? Tell me. At least give it a try. Mohit Jha. Any thoughts on this? Anyone? Arnav Mandal? Okay, so at any iteration, suppose this is your zeroth row, any iteration, can we have a negative value in primal simplex in the right hand side?
No.
It has to be positive, greater than equal to 0. So what does that mean? It maintains primal feasibility iteration after iteration or not?
Yes, sir.
We also talked, except at the final iteration, the value of y1, y2, ym, are they feasible other than the final iteration? Are they feasible to the dual problem or not?
No, sir, they are infeasible.
They are infeasible in the primal scales. What we do, we maintain this primal feasibility. That means RHS is always greater than equal to 0 and try to achieve that y1, y2, ym, the dual variable become feasible to dual problem. The moment both of them are feasible, we say that we are at the optimal solution. This is for primal simplex. When we talk about dual simplex, your y1, y2, y3, ym, they will be feasible to your dual problem, but on this side you will have negative values. The moment all the negative values are gone, it will become primal feasible, right?
Yes, sir.
The moment it becomes primal feasible, this is always maintained as dual feasible. So whatever y1, y2, ym value you will see under the slack variables in the zeroth row, for dual simplex, it will always be a feasible value. So let's try to understand this with the example. First, let me give you the algorithm. So dual simplex algorithm. First step is initialization. Convert a minimization problem into first maximization problem. Convert, this is one, any greater than equal to less than equal to by multiplying minus sign. Minus not sign, minus one both side is more appropriate to write. Okay, so for example, suppose if I give you, I'm not saying whether it is a, when I say dual simplex, it does not mean it has to be dual, because any dual is dual of someone or primal of someone. So if I just give you a problem, 4x1 plus 12x2 plus 18x3, x1 plus 3x3 is greater than equal to 3, and 2x2 plus 2x3 is greater than equal to 5, x1 2x3 greater than equal to 0. Can you recognize this problem? Which problem is this?
Dual.
Dual of Binder-Glass problem. But I'm not telling you whether it is dual or anything. I'm just giving you a problem which has minimization greater than equal to constraint time. So first you need to put it into the standard form. So you will put it maximize minus g equals to minus 4x1 minus 12x2 minus 18x3. So minus g plus 4x1 plus 12x2 plus 18x3 equals to 0. Your zeroth equation. This constant will convert into less than equal to, so minus x1 minus 3x3 plus a slack variable x4 equals to 0. 2x2 minus 2x2 minus 2x3 plus a slack variable, because now this after multiplying with minus, this constant is converted into less than equal to. So I need to add a slack variable equals to minus 5 and minus 3 here. So okay, so now you have put it in the standard form to work with dual simplex, because as I said, it is invoked when you have negative RHS. So you can see you have two negative RHS here. So this is invoked. Now, so first step is initialization. What is second step in the primal simplex algorithm? Once we initialize, what do we check?
Optimality.
Okay, so correspondingly to optimality, the test here changed to feasibility. Feasibility test. So feasibility test says if all basic variables values, that means RHS value, are non-negative, then stop. Solution is feasible and hence optimal. Solution is feasible and thus optimal. So now optimality test has been converted into feasibility test. All I need to check that right hand side has become positive or not. Now coming to iterations. So please. Third step is, as you are aware, we'll do the iteration. So you already know primal and dual. Dual, more or less, it is symmetric transpose of primal. Do you agree? Here we write CX, here we write YB. Here we write AX, here we write Y transpose A. Right? So in some sense, it is a transpose. So we will start with, instead of entering variable, we look for leaving basic variable. So leaving basic variable works with the select the most negative RHS. Okay, select the most negative RHS value as the leaving basic variable. Then who will be entering? Minimum ratio test to be performed only for non-basic variable with negative coefficient in the pivot row. Select one with smallest absolute value of ratio. Then next step is, as usual, new BF solution. Solve for the new basic solution. So once again, for leaving basic variable, we'll look at the right hand side. Instead of the 0th row, we'll look at the right hand side. Earlier we were looking at here for the entering basic variable. Now we'll look at the right hand side, look at the most negative value that will leave the basis. Entering basic variable, suppose if this is the pivot row, the ratio is calculated between the gth row coefficient and this pivot row coefficient only for non-basic variable with negative coefficient. Let's try to solve it. So let me first write down the equations. So minus g plus 12 plus 4x1 plus 12x2 plus 18x3 equals to 0. My equations are this is my 0th equation, minus x1 minus 3x3 plus a slack variable x4 equals to minus 3. First equation, minus 2x2 minus 2x3 plus a slack variable x5 equals to minus 5. Second equation. Iteration basic variable equation g x1 x2 x3 x4 x5 right hand side. Okay, so iteration 0. Let's put the values. Basic variable g. What are the basic variable at this iteration?
X4, X5.
X4 and X5. The slack variable remains the basic variable. Equation 0, 1, 2. G equals to minus 1 because it is a minimization problem. Now let's put all the coefficients 4, 12 and 18, 0, 0, minus 1, 0, 0, minus 2, minus 3, minus 2, 1, 0, 0, 1, 0, -3, and -5. Okay, so we have initialized it with the x4 and x5 for equation 1 and 2 as basic variable, g as equation 0 basic variable. Now tell me feasibility test. Is this solution feasible?
No, sir.
Why it is not feasible?
RHS all are negative. Like
We
they
have
should be
negative
not.
values in the RHS value, so it is not feasible. So among these two, this is the between -3 and -5. This one is the largest, right? This is the most negative value. So look for the most negative value. So -5. So your x5 is the leaving basic variable. And highlight this pivot. Now, I mean, if you look at it, it is exactly looks like your simplex algorithm only, but now you are looking from the this is the right hand side, not from the top. You are looking at the simplex algorithm from right hand side and not from the top. Here we will calculate the minimum ratio. So tell me, for which variables I can calculate the minimum ratio? Read the statement.
Basic variables.
Okay, very simple logic. The basic variables which are already in basis. Do we need to calculate any minimum ratio for them? Who can enter the basis? Basic variables or non-basic variables?
Non-basic variables.
So what does it say here?
Only
For the non-basic variables, right? And that too with negative coefficient. So let's try to calculate so the non-basic variables right now is x1, x2 and x3, right? x4 and x5 is a basic variable. So let's look at, should we get a minimum ratio for x1 column? Should we calculate minimum ratio for the x1 column? No. What does it say? Only negative coefficient. Do we have negative coefficient for x1 column?
No.
So we'll just put a small dash here. Now coming to x2, we have a negative coefficient. So we'll do 12 by -2, that is equals to -6. For x3 again I have a negative coefficient, so 18 by -2, which is equals to -9. For basic variable we will not calculate. So among these, which one is the minimum?
-9.
Smallest absolute value. Which one is the smallest absolute value?
-6. Go 6.
So x2 will enter the basis and this becomes my pivot column. Good so far? Any questions? Question 1. So G x4 instead of x5. Now I have x2 entering the basis 0, 1, 2, -1, 0, 0. Okay. So once you got this, I want you to, as our standard practice, this should becomes +1. Everything above it is 0. Go ahead, complete the put it in a proper Gaussian elimination form. Put x2 column into proper Gaussian elimination form. So the pivot cell should become 1 and everything else above and below it should be equals to 0. Go ahead, do it. Right. Okay, let's look at the pivot row. So what I need to do to make this coefficient 1? What exactly I need to do to make this coefficient 1 here? Divide by how much?
-2.
You need to divide this whole row by -2 so that this coefficient becomes 1. So I have divided the -2. So -2, 1, 0, -1 by 2 and 5 by 2. Is this correct? Now I need to ensure that the everything above it is 0 so that it becomes it can be in the proper Gaussian elimination form. Since we already the equation 1 there is a 0 here, so I don't need to do any changes. I will copy it as it is from the top. Now coming to this part, I need to make this 0. So how much I need to multiply this equation with? 12. So what I will do, I will multiply this equation by 12 and subtract from the first equation. Earlier we used to add because coefficients were negative. Now we will be subtracting. So we'll multiply it with the 12 and subtract from the first equation. So this into 12, 4 minus 12 into 0 remains 4. 12 minus 12 becomes 0. 18 minus 12 becomes 6. Again 0 here, so x4 is still a basic variable, no need to worry. 12 into -1 by 2 is -6. -6 and -6, 6. 12 into 5 by 2 is -30. Is this correct, guys? Devika, you want to tell us something? Devika, is it correct? Devika, we cannot hear you. Is the iteration 1 correct or not?
Sir, am I audible now?
Yes, you are. You have any questions?
No, sir. I got the same thing.
Okay. Now, interesting thing I want you to highlight here. Look at this one, 1800. Check whether it is feasible solution to this problem. Okay, dual of this problem would be not x3. x3 is a part of solution. My bad. Just hold on. So x1, x2, x3 are original variable, right? And x4, x5 are your slack variable. You already know dual of this problem is what? Maximize g equals to 2x1 plus 5x2. x1 is less than, I'm putting it in x1, I should put it in y. Maximize g equals to, actually the window glass problem. x1 is less than equal to 4, 2x2 is less than equal to 12, and 3x1 plus 2x2 is less than equal to 18. So this is the dual of this problem. Whether 0, 0 is being satisfied or not by the dual problem. Whether 0, 0 is being satisfied with the dual problem or not.
Yes, sir, satisfied.
This is nothing but corresponding y1 and y2. Okay, so you can see if you plug in, okay, why I'm writing it as x1. If you plug in this 0 and 0 here, you will see it is being satisfied. As far as -3 and -5 is concerned, if you plug in into the original problem, -3 and -5, if you plug in -3 and -5, is it feasible?
No, sir.
So this is what I wanted to highlight. Your dual solution is feasible, primal is infeasible. So try with 0,6. You already know Winter-Glass problem 0,6 is a optimal solution, feasible solution, right? But
Yes, sir.
minus 3 and 5 by 2 again is not feasible to this problem. So far you are maintaining the dual feasibility, but your primal feasibility is not maintained. The moment both the feasibility is stored, it will be optimal. Earlier, if you remember primal simplex, we were maintaining the primal feasibility, but dual feasibility was not maintained. If you remember last class we discussed each point we have checked in the simplex iteration, and that was not being maintained. So what I want you to do now, again, calculate the minimum ratio. But before that, which one will enter the leave the basis now? Let me ask someone. Akanksha Agrawal, can you hear me? Akanksha Agrawal. I keep asking A guys. Let me ask some. Tushar Punia, can you hear me?
Yes, sir.
Tell me which one will leave the basis now at the first iteration?
X4.
X4 will leave because there is only one negative number. So X4 will leave. Okay. Pragati Sahu, can you hear me? Pragati Sahu? Mohit Kumar Jha, can you hear me? Every time I'm calling your name, I'm recording it for my teacher's assessment. Keep that in mind. Okay, Vaibhav Darsarath. Vaibhav just logged out. Okay, whoever wants to tell me for which variable we'll calculate the minimum ratio here.
Non-basic variables.
Non-basic variable. Which one are non-basic variable at this iteration?
X1, X3, and X5.
X1, X3, and X5. So X1, X3, and X5. Among them, for X1, I can find 4 by minus 1 equals to minus 4. For X2, it will be dash, it is a basic variable. For X3, it is 6 by minus 3, that is minus 2. For X4, again, it is a basic variable, a dash. And finally, X5. Should we get anything for X5?
No, sir, it's not negative.
It's not a negative coefficient, so you'll just put a dash here. So among these, which one is the minimum? This guy?
2.
X3. Yeah, minus 2. Yeah, right. So now X3 will enter the basis. So iteration 2, G, X3, X2, 0, 1, 2, minus 1, 0, 0. Complete this iteration. Yes, David, you want to say something?
No, sir.
Okay, so this one, we need to make this coefficient 1. So we'll divide it with -3. If we divide it with -3, we'll get 1/3. Color is not good. 1/3. Then this 0 remains 0. This becomes 1. This becomes -1/3, 0. And this guy becomes 1. Below it and above it, both there are coefficients, so we need to write it properly and subtract it every time. So we will get 2, 0, 0, 2, 6 minus 1/3, 1, 0, 1/3 minus 1/2. Here we will get -36, 1 and 3/2. Did you guys get that?
Yes.
Have you passed the feasibility test here? All RHS is greater than or equal to 0?
Yes, sir.
We have found our what do you call it? Feasibility. Now,
Yes,
if you look carefully, what is this 2 and 6?
optimal solution of Winter-Glass problem.
Winter-Glass problem. So what we have seen, this is the problem which we have tried to solve, which is actually dual of Winter-Glass problem. But as I said, dual of dual is primal of prime. So this is the problem we are trying to solve. And its dual was maximize W equals to 2y1 plus 3y2. y1 was less than equal to 4, 2y2 was less than equal to 12, and 2y1 plus 3y2 was greater than equal to 18. So for this problem, if you remember, when we solved Winter-Glass problem, we used to get 0, 1, 3/2 and 1. So this is the solution to this problem, and to this solution, 2 and 6 is the solution to this problem. Clear? Interesting? It is mostly actually algebra only, but the way we use algebra to solve or construct a simplex algorithm is actually interesting part. So any question in dual simplex algorithm? So what is the benefit of dual simplex algorithm?
Greater than sign and RHS negative, you can
So if
proceed
RHS
with.
negative, if it is greater than equal to sign, even if it is equals to sign, if it is equals to sign, what do we do?
We write two constraints, greater than and
Right,
less than.
greater than equal to, 1 less than equal to, greater than equal to, we again multiply with minus. So this takes care of all those big solving those equations, two-phase, first phase, two-phase, everything is being taken care of if you apply this problem. So if I give you a problem which is ill-behaved and I do not mention anything that you use big M or two-phase or dual simplex, which one you prefer to use? Which one you will prefer to use? Suppose I give you a minimization problem with greater than equal to constraint and equal to constraints. Or suppose the problem which I have solved teaching you big M and two-phase, that 0.5 into x1 plus something like that. Now if I give you this problem and do not mention anything in the question that whether it is you need to solve it using big M or two-phase or dual simplex, which method you will prefer to solve it with?
Dual.
Itna is why so lamely? Okay, hands up for dual simplex. Raise your hand. I was expecting all of you will raise your hand, right? Okay, Anurag. Anurag Raj, can you hear me? Anurag J. Raz or Anurag Vaibhav or Akil Ahmed or Arnav Mandal. Can you guys hear me? It is impossible that I call 5 names and none of you can hear me, okay? Okay, people who have raised the hand, why do you think it is better than Big M and Two Face?
Sir, in big game we should add m and we should do some more calculations. But here, if you'll put a minus sign, then minimum will change. Minimum will change to maximum.
Okay.
I mean the objective function. And
But that is objective function only. What about other equations?
So like we have to introduce the artificial variable, but here no such.
So first, biggest advantage is you do not need to deal with artificial variable. Suppose if you deal with the artificial variable, if m comes, then artificial variable also appear in objective function, then you need to subtract those equations to remove artificial variable from the zeroth equation. You remember, before you start, you have to do all these things. If you are doing two phase, then you have to first solve the first phase, then go to the second phase. So again, painful exercise. Here, it is like a regular simplex only. Now, instead of looking from the top, now you are looking from the right hand side. That's the only difference, right? So that is my personal opinion that dual simplex, if I have been asked such question, I would rather use the dual simplex, but it is definitely up to you. Until and unless it is not mentioned that what method you need to use, you can use any of the method which you are comfortable with. Okay, guys.
okay, sir.
Yes, sir.
Any questions? Let me try to export. If PDF is automatically updated, otherwise I will upload it. So, okay, so we'll take a break. We'll start again at 12. We'll start the new topic called sensitivity analysis. I will only teach it for half an hour, and then if you have any questions for class test 1, we can discuss that. Okay, take a break. Okay, guys, let's start sensitivity analysis, the new topic. So, what are the parameters or known constant in any linear program? What are the parameters, guys, for any linear program? So in this linear program, what are the parameters you should be knowing in advance? Then only you can formulate this program.
Decision variables, constraints.
Decision variables are parameter or decision variables? They are known or unknown?
They are unknown, sir.
They are unknown, which you try to find while solving a linear program. But suppose if I do not give you C, A or B, can you formulate a linear program?
No, sir.
No, sir.
So these are the known parameters. Without them, you cannot formulate a linear program. So now C is a cost or profit coefficient. A is your technology matrix. And B is your resource label, how much resources you have, right? Now suppose, let's start with B first. Suppose you have one machine in your plant, right? You formulated this problem and you solved it. You know how much of product 1, product 2, product 3 to manufacture. Is that correct? Now, if you add one more machine in your plant, is this formulation becomes invalid? You understood my question? If I add one more, suppose like window glass problem. If I have 4 hours in plant 1 and 12 hours in plant 2, 18 hours in plant 3. I have added one more machine in the plant 1, so that now I have total 15 hours or 10 hours or 8 hours available. In that case, this linear program becomes invalid, which we have solved earlier. Is that correct?
Yes, sir.
So any parameter, I just gave an example of A, any parameter is actually an estimate. It is an estimated value, right? Like technology matrix. Suppose when I'm writing window glass problem, 1 into x1 or 2 into x2 or 3x1 plus 2x2. So what it is asking, I want to produce product 1, I need 1 hour. To produce x2 product 2, I need 2 hours. Suppose I have made some operational changes. Instead of 1, it is taking 1.5 hour. Instead of 2, it is just taking 1 hour. It is taking 3 by 2. It could be that I have added, instead of 1 person working at that machine, I have added 2 person working at that machine. That has made it faster. So technology matrix changes. Similarly, cost profit coefficient is generally given by the marketing department based on the demand in the market. If I sell product 1, I will get a profit of 3 rupees. If I sell product 2, I will get a profit of 5 rupees. So these are the estimate. Many a time we do demand forecasting, where your time series modeling, machine learning models are used to estimate what would be the demand in the market for a product in coming months, right? So these are estimate. The problem with the estimate is, if it is a current state, there could be inaccuracies and bias. In future state, it can be uncertainty and bias. Bias generally come from many of the qualitative method. Like for forecasting, one of the method is Delphi method, where experts sit together, all sales VP of sales sits together with the all sales manager and tries to take their feedback, what is in each region, how our product is performing. So each of the individual have their biases, which may change the product. For example, for future state, suppose a sanitizer company, just giving a very recent example, a sanitizer company was producing sanitizers based on the market demand at that time. Suddenly COVID came and the market demand went up. No, a huge surge. The profit, cost, everything has changed. Now the problem is a company which has already kind of like production planning for next 1 year. They have already decided that this many resources I need. So definitely based on that, they have asked for raw materials and everything. But suddenly demand surges and this linear programming model based on which the production was done is now useless. So what we want to understand, this linear program should not become useless. Just based on the last solution which I have found, I try to accommodate the new changes and where all I can accommodate those new changes. So there are two possibilities for parameters. First is how sensitive this parameter. If it is insensitive, to what degree it is insensitive? So the linear program which you have solved using simplex, there are two situations. Either you find allowable range to stay optimal, excuse me, or you try to find allowable range to stay feasible. Now coming back to our standard structure of simplex, CB, B inverse A minus C, B inverse A, CB, B inverse, B inverse, CB, B inverse B, and B inverse B. You have your G here and basic variables here. Right? So this is how we know our simplex table. Now, when I say allowable range, what we really want to know that given any change in the parameter, like B value is increased by 1 unit or 2 units, similarly, C value is changed or A values are changed, does my basic variable change? I'm not talking about their values will change. What we want to know, if any of the parameters changes, whether my, suppose right now my basic variables are x1 and x2, they are related to the activities which I do. What are the activities? Produce product 1, produce product 2. But if my basic variable becomes x1 and x3, where x3 is a slack variable, there is only one activity that I need to do, which is produce product 1, no need to produce product 2. So what we want to know, whether my basis remains same, keeping the solution optimal or feasible. Are you guys following? Their values, definitely, if I make changes in B, their values will change. But my basis should remain same. Maybe x1 and x2, which is 2 and 6 right now, may change to 5 and 3. But basis should remain same. So that is the idea. Now looking at this structure which I have written for simplex, what do you think? For which variables I need to find the allowable range to stay feasible, and for which one I need to find allowable range to stay optimal? If I make any changes in B vector, RHS value, where does it affect? Optimality side or feasibility side? If I change small b, which area it affects? The feasibility side, the optimality side?
I think feasibility side.
Only the feasibility side, you are right. Here we need to ensure that whatever value I change, it should be greater than or equal to 0. Now, if I change a value of C, where does it affect?
Optimality, sir.
Optimality side. If I change the value of A, where does it affect? It again affects the optimality size. See, A is here. If I do a new CVB inverse A minus C, and if suppose at the optimal table, what I will have the values, all of them is greater than or equal to 0 or not, right? If I make some changes in A and some of the coefficient becomes negative, then they can enter the basis, right? My basis will change. Are you following?
Yes, sir.
So that is the difference. So now we will treat each one of them individually. So I will start with the first change in the RHS value. That is change in the B. Let's see how it affects. So suppose my original problem was maximize G equals to 3x1 plus 5x2, x1 being less than or equal to 4, 2x2 is less than being equal to 12, and 3x1 plus 2x2 being less than equal to 18. Now my current B vector is 4, 12 and 18. Now I have invested some money and found out that now I have 24 hours in plant 2. What would be the effect? So first we need to understand what is the last known solution to, what is the last known optimal solution. So I will just write the last iteration of the Winter-Glass problem. So last known optimal solution is G x3, x2, x1, x1, x2, x3, x4, x5 and RHS. So 0, 0, 0, 3 by 2, 1, 36, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1 by 3, 1 by 2, minus 1 by 3, minus 1 by 3, 0, 1 by 3, 2, 6 and 2. This is the last known optimal solution for this problem. But now the problem has changed because one of the constraints now is 2x2 is less than or equal to 24. So if you do not know anything, what would you do? You will start everything again with 2x2 less than or equal to 24. Is that correct?
Yes, sir.
So what we need to do is, let's look at this table. Where exactly B is affecting. These are the 2 points B is affecting. So I will first calculate new B inverse B. Let me call it B new, this guy. So my B inverse is here. So 1, 1/3, minus 1/3, 0, 1 by 2, 0, 0, minus 1/3, 1 by 3, and B new is 4, 24 and 18. Give me the new values for this one, and also CB, B inverse, B new. So we have CB, B inverse here. So 0, 3 by 2 and 1, and B new is 4, 24 and 18. Give me these values. Do a quick multiplication. Tell me how much you got.
6, 12 and minus 2, sir. B
6,
inverse B.
12 and minus 2. Here you will get how much? Okay. So what we will do, we will do these changes directly in this last known optimal solution. So x1, x2, x3, x4, x5, g, x3, x2, x1. RHS. So there are no changes in this side, inside it. Does not, B does not affect any of these. So we will calculate 0, 0, 3 by, sorry, 0, 3 by 2, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1 by 3, 1 by 2, minus 1 by 3, minus 1 by 3, 0, 1 by 3. Now with the new B, this becomes 54 and this becomes 6, 12 and minus 2. We need to re-optimize it, because why I need to re-optimize it? Can x1 value be less than equal to 0? Is it possible?
No, sir, it's not possible.
So that makes it infeasible. So I need to re-optimize it. But luckily, I don't need to start from the scratch. Whatever last known solution I know, from there I will proceed. Okay, given if a table is in this form, how would you proceed? How do you proceed when RHS becomes negative? How do you proceed when RHS becomes negative? Remember this method?
Yes, sir. We'll multiply with minus 1 all the equation.
Nothing, you don't need to do anything. You have a negative RHS, you will simply invoke dual simplex from here. No need to change any equation, anything. This is the only negative value, so x1 will leave the basis. Try to find the minimum ratio. So 0 by 1, not actually x1, x2 and x3 are basic variable, no need to do anything. Do 3 by 2 divided by 1 minus 1 by 3. How much you get? 3 by 3, 9 minus 9 by 2. Is this correct? The moment you see in the simplex table, the negative value like this, after for re-optimization, you need to use the dual simplex method. You already know the method. So this is the only negative value you have. So which one will enter the basis?
X4.
X4 will enter the basis. Do the re-optimization. Tell me what value you get. X3, X2 and X4. Do the re-optimization. Tell me what values you get. So you should get minus 3, 0, 0, 1, minus 1 and 6, 2, 3 by 2, 1, 0, 0, 1 by 2 and 9, 1, 0, 1, 0, 0, 4 and 9 by 2, 0, 0, 0, 0, 5 by 2, 45. Is it matching?
Yes, sir. It's matching.
Let's see what exactly has happened. Let's try to understand it graphically. So our earlier problem was this space. So actual window glass problem, we had 3 constraints: 6, 0, 0, 9. Okay, and 4, 0. So this was constraint number 1. This was constraint number 3rd, and this was constraint number 2nd, and this was our feasible region initially. Let me use this constraint with dotted line because we will change it. So this was your. So this was 2x2 less than equal to 12. This was x1 less than equal to 4, and this was 3x1 plus 2x2 less than equal to 18. And based on that, our solution was 2, 6. Remember that?
Yes, sir.
Now what we have done, we have changed this constraint from 2x2 less than equal to 2x2 less than equal to 24. Can you tell me the intersection of line 3x1 plus 2x2 and 2x2 less than equal to 24? What is the point you will get? These two lines?
Minus 2, 12.
Minus 2,
Minus
comma.
2.
12.
What did you get here?
Yes, sir. Minus 2, 12. X1 equal to minus.
Got x1 as minus 2 and x2 as 12. But that was infeasible because now your feasible region, which was earlier until this point, now have changed to this one because this line has disappeared. So solution actually is happening at 0, 9. So you understand how you re-optimize? You brought it from here to here. That is the solution you have got. X2 equals to 9, x1 equals to 0. Does that make sense? Understood, guys? Whoever is planning to paying attention, how things changed, algebraically. Algebraically, you have found it here, minus 2 and 12. Graphically, you can see where the new intersection point is. Fair enough? Okay, so this is if I give you a particular value and ask you to check whether, so ideally when I say re-optimize, your basis changes. Did the basis change here or not? Did the basis change from the what you were doing earlier and now what you are doing? The basis has changed or not?
Yes, sir. Basis change.
Yes, sir, it has changed.
Earlier, X1 and X2 both were your primary activities. Now only X2. You are producing only product 2. You are not producing product 1 anymore. But as I was talking about allowable range, so I want to understand allowable range for current best known basis to remain feasible. What should be that allowable range? That even if I increase until that point, my basis does not change, its value might change. How can we find that? So suppose I have a B right now, 4, 12 and 18. I have a delta B plus delta B. I have done 4, 12 plus delta B2 and 18. And I will try to find what is the range of that delta B2 in which your X1, X2 and X3, which is the current basis, remains feasible. I don't need to change my basis, values might change. How can we find the range of delta B2, guys? Any suggestion? So where does your B new affects? B inverse B new? You agree? Look at the table. This is where B affects or not. If I want to remain feasible, whatever this quantity be, what should be the sign of this quantity?
Positive.
If I want to remain feasible?
Positive, sir.
Greater than
Positive.
equal to 0. So as long as B inverse B new is greater than equal to 0, my basis remains same. So take whatever the last known best basis you have. So I have taken B inverse from that table. And I have multiplied it with 4, 12 plus delta B2 and 18. And this should be greater than equal to 0. If you multiply this, you will get 3 equations. 2 plus delta B2 by 3, 6 plus delta B2 by 3, and 2 minus delta B2 by 3. All these should be greater than equal to 0. Now tell me what is the range of delta B2 from these equations, in equations.
-6 to 6, sir.
You will get delta B2 between -6 and 6. Let's look at each one of them. Delta B2 by 3 should be greater than equal to -2, which is delta B2 should be greater than equal to -6. From this one, you will get delta B2 should be greater than equal to -12. From this one, you will get delta B2 should be less than equal to 6. -6. So based on that, delta B2 is, so corresponding B2, which is right now at 12, any value between 16, 6 and 18 will not change your basis. Definitely B values, I mean basic variable values will change because you are multiplying with a higher number other than or lower number than the B2. But as long as you keep 6, 12, 18, it will not change. I will quickly show you something. Just give me a second. Can you see the window glass problem which we have solved using Excel? Can you see my screen, guys?
No, sir, we cannot see your screen.
Not yet. Let me just check again. Can you see it now?
Yes, sir.
So I will go ahead and try to solve this one. Data solver, and I will solve it. So when this pop-up appears, try to see few things. It says keep solver solution. Okay, you ask for sensitivity. Can you see in the report sensitivity?
Yes,
You
sir.
select that and click OK. So along with 2 and 6, the answer, and 36, you will see a new tab has also appeared, that is called sensitivity report 1. Can you see that? A new worksheet. If you go in that worksheet, it will show you the allowable ranges for everyone. So for 12, you can see allowable increase is 6 and allowable decrease is 6. For similarly for B1, B2 and B3, you can give the values. So it has taken the name C1, C2, but it is not really C1. It is giving you the constraint on right hand side 4, 12 and 18. Right now we have just found 12 minus 6 is 6, 12 plus 6 is 6, 18. So 6 to 18, or delta B2 is minus 6 to 6. Similarly, you can find for B3. Similarly, you can find for B1. Is this correct, guys? Understood? Here it is actually thoda sa naming mein gadbad ho gaya hai kya? It is not understanding. Ideally, it should have been showing these are the C parameter values. Tumhara how much of profit or cost coefficient you can increase or decrease. That is the next topic we will study. So going back, understood how sensitivity can be generated with the Excel? So you guys can try on your own. You already have this Excel sheet on the Teams. You can download it, or you can write your own, and you can do the needful. Now let me show you one more thing. So one thing to keep in mind when you are noticing that, first one is you can only change if you are trying to find the allowable range. You can only change B parameters, B values one at a time. What does that mean? Suppose I want to find the allowable range. I have already done B plus delta B2. Let me show it here. 4, 12 and 18 I have done into 4, 12 and delta B2 and 18. Next, whatever delta B2 you have to keep. Now, if you want to understand the allowable change in B1, you have to do 4 plus delta B1 and other remains constant. If you want to find for B3, you have to do 4, 12, 18 plus delta B3. If you try to do all of them together, 4 plus delta B1, 12 plus delta B2 and 18 plus delta B3. Suppose if you try to do this, what is the issue you will face? Can you tell me what is the issue if you try to do the simultaneous change? What is the issue you might face? Any thoughts? if I try to change all of them simultaneously to find the allowable range to remain feasible, what is the issue I might face? Or can you find it?
Like inequalities containing three variables, delta b1, delta b2, delta b3.
Very good. So there are three inequalities with three unknowns. It is difficult to find, right? Had it been equality, you could have find it. But all these things are greater than equal to 0. You cannot solve for them simultaneously. So whenever you want to find the allowable range, each one will be treated separately while keeping other constant. Like what I have shown you here. Any questions, guys? But there are situations, this is for allowable range. If I give you 4, 12, 18 changes to 8, 24 and 32. Here I'm not asking for allowable range. What you need to do here? I'm not asking for allowable range. I'm already giving you the values which I have changed. What can happen? B inverse B new. If everything is greater than equal to 0, whatever solution you get is the value of your X basis. If B inverse B new, if any one of them is less than equal to 0, you need to re-optimize using what? How do you re-optimize? Dual simplex. Okay. Any questions? So two interesting concepts which we have studied today. First is dual simplex algorithm that helps you in solving ill-behaved problem without using artificial variable. And second is, if I change my right hand side slightly, how much I can change? That is the first thing that falls under allowable range of feasibility. Second thing is, somebody tells you this was the increase, tell me the solution. Then you have to do the B inverse B new. You have to find the CB inverse B new, and then plug those values directly into the last known solution to you and re-optimize. Clear? Any questions, guys? Any question from dual simplex? Okay, if not, let's revisit what we have studied until last week. That will come in your syllabus. So tell me topic one after another. What is the first thing which we have studied?
Formulation.
We have studied LP formulation. Okay, we have seen different kind of formulation. You also tried some of the formulation in your homework. So just to repeat, when you are formulating, first thing you need to ask, what decision we want to make and how it affects my objective. Once you understood your decision variable, formulation becomes easy. It can be maximization time, it can be minimization time. After formulation, what we have studied?
Graphical method.
We have studied graphical method. It can be maximization type, it can be minimization type, it can be greater than equal to constraint, it could be less than equal to constraint, it could be equal to constraint, but only for two variables. Right? So what you need to do, you have to draw the graph and then find the sign of direction of feasibility you have to find. and then direction of increase or decrease you have to find. The best way to find direction of feasibility, what have been taught? Plug in origin and see if it is satisfying. So any constraint less than equal to or greater than equal to, plug in the origin 0, 0 and see if it is satisfying. If it is satisfying, the direction of feasibility is towards 0 or towards center. If it is not satisfied, direction of feasibility is away from your center origin. If the constraint passes through the origin, then how do we find?
So any other point?
Take any other reference point, check whether it is contained in that feasible region or not, and you can proceed. So this is about graphical method. Then we have looked at algebraic simplex. So I will take all of them together: algebraic simplex, tabular simplex. Method wise, both are same. At one place you do the equations, in one place you only work with the coefficient. As far as simplex algorithm is concerned, what you check, you initialize, I'm talking about standard form, you initialize with origin, that means slack variables form the basis. Then you have to look at entering basic variable, 0th row coefficient or 0th row negative coefficient you need to look at. Then that will be your pivot column. Then you need to look at the leaving basic variable. For leaving basic variable, you find the minimum ratio and identify the pivot cell. Put in the Gaussian elimination form. What are the special cases you can find in tabular simplex?
Tie in entering basic variable.
Tie in entering basic variable, tie in
Leaving basic variable.
leaving basic variable. What is this phenomenon called? Leaving basic variable tie?
Easy.
I have given one example. Try to solve and see how it goes cyclic. Both of them break the tie arbitrarily. Don't worry. Whatever problem I will give you, it will have a solution. It will not enter in the cycle. Then unboundedness. And finally, put it in different stuff. Multiple optimal. How do I find unboundedness in the simplex table? Minimum ratio, you cannot find the minimum ratio because no entering basic variable, right? Others?
Yes, that's right.
How do we find the multiple optimal solution in the simplex table?
The non-basic coefficient becomes 0.
Non-basic coefficient in the 0th row becomes 0.
Yes, sir.
Is this correct, guys? But you have to add one more thing here. Non-basic variable coefficient become 0 in the 0th row in the final iteration, right?
Yes, sir.
Okay. What is the other way without even solving, at least for classroom problems, which we do not deal with 100,000 variables and all that? How do we know that we have a multiple optimal solution? You have not even started solving the problem. I have just given you a question. You look at the question and you know it will give me a multiple optimal solution.
The objective function is similar to one of the constraint.
Similar name, parallel.
Yes, sir, parallel.
Parallel. So if objective function is 3x1 plus 3x2, one of the constraint is also 3x1 plus 3x2 less than equal to something. So there only itself you should be able to recognize that I have a multiple optimal solution. And whenever there is a multiple optimal solution case, you have to find the both of them. You cannot just leave at the last whatever you get and say that okay, there are multiple optimal solutions. You need to find that multiple optimal solution also by doing one more iteration, forcing that non-basic variable to enter the basis. So I guess that was the gist of all the simplex algorithm we have seen. What did we do next?
Ill-treated problems. Ill-treated problem.
Ill-behaved problem.
Ill-behaved, yes, sir.
I mean, they are not really ill-behaved problem. We are calling them ill-behaved only because our standard form is like that. So ill-behaved problem, you will see minimization type. You will see greater than equal to constraint. You will see equals to constraint. Minimization types are easy to handle. Just multiply with the minus. For greater than equal to, first subtract a surplus and then add a artificial. For equal to type, add a artificial variable. Right? After you do this operation, remember that G equation should be free from basic variable, because basic variable, or I'm also putting more precisely artificial variable, because artificial variable will come into your basics because you are either multiplying with this one. I'm talking about only big M. Okay, what happens because you are adding artificial variable below, you are multiplying them with big M in the objective function value. Now artificial variables are your basic variables also and present in the zeroth equation also. So we subtract those artificial variable and then proceed. As far as two phase is concerned, first phase, minimize sum of the artificial variable. Second phase, you need to delete corresponding columns from the table. Put actual objective function coefficient. Put it in a proper Gaussian elimination form. Proceed with the iteration. So this is big M and two phase. Now, if a problem is infeasible, what will happen in big M and two phase? If a problem is infeasible, you are trying to solve it, what will happen?
At the final iteration, I think artificial variables will not remain 0.
Yes. Tomorrow, what will happen that the artificial variable will have a positive value in your final iteration. Final iteration means if you are solving a big M, you have all the zeroth row coefficient has become positive. If you are solving it using two phase, then if you are solving using two phase, then what do you call? the row coefficient again has become all greater than equal to 0 and artificial variable has a greater than 0 value. Then you can stop there and the first phase itself and say that this problem is infeasible. No need to invoke second phase. Okay, what is the next topic we have seen after that?
Revised simplex.
So revised simplex, as far as revised simplex for this course is concerned, just keep in mind this one, CVB inverse and all that. I can give you any basic variable at any iteration, can ask you to, give me the solution at that point. Generally, I do not ask any problem to be solved using completely using revised simplex method. I will give you some basic variable, or I will give you B vector or B inverse vector, and I will ask you to complete that iteration. And finally, duality. Duality, until how much I have said that I will ask in exam? Formulation.
Finding dual from primal.
Yeah, formulating, not formulating, formulation is a long term here. Converting primal to dual. So already I have given you a table. Based on that, you can convert any primal problem into the dual problem. After that, whatever I have taught, I will ask in class test 2. That will take care of your what do you call all the theorems. Then dual simplex method, sensitivity analysis, and by that time I might have covered transportation and assignment problems as well. So any questions? Although I'm scheduling your test for 25th of February, that is a Friday. I will be available on Thursday, not Thursday, Thursday would be too late, I guess. I will be available on Thursday, 9 to 10 a.m. I will be logged in. If you have any questions, you can log in and discuss with me. Okay? Any questions, guys? Any questions, guys? If there are no questions, best of luck for your exam. And I have also uploaded few documents yesterday. There are practice problems and everything. If you want to practice from there, you are free to practice. And if you have Hiller and Lieberman, you can practice any question if you want to. Thank you very much. I will see you. Yeah, as far as exam is concerned, it will be exactly like the assignment, but it will be time bound. It will appear exactly around 11 a.m. on that day. And if I give you 1 hour or 1.5 hours or 2 hours, at that time it will close. After that, you will not be able to submit. If I'm giving you 2 hours, that means 1 hour 45 minutes is given for you to work on the problems. Last 15 minutes to take the photographs and upload it on the Teams. If you send after 2 p.m. 1 p.m. if it is the due time, I will deduct some penalty, and that too within if you send it to me within 10 minutes, I will deduct some penalty. After 10 minutes, like 1:10 p.m., I will not consider at all. If you are copying or helping someone copy and I find it, I will give 0 to both of you, because assignments were checked by the TAs. All, in fact, split between TAs. All the quiz class test 1 will be checked by me. So if I find that at any point of time you have copied from someone or you have helped copying someone, both of you will be getting 0. I do not care who has helped and who has not helped. So तुम्हारा जो भी WhatsApp group है जितना उसमें share करना है कर लो. But keep in mind that if you found to be cheating, I will give a 0 for that. Okay, fair enough. Okay, thank you very much, guys. I will see you week after. Bye-bye.
Thank you, sir.
Bye.